We're going to take a look now at predicting redox reactions in solution. This is the second part of our predicting redox reactions video, and this part is a little bit more of an extension on what we did in the first part of this video lesson. So we're going to take a look at how we can use that spontaneity rule that we talked about and what that means when we're looking at more complex reactions. So there's a few steps that we need to look at before we actually go into an example. So the steps to determine or predict a redox reaction in a solution is to first list all entities present. So a few things to keep in mind is that if something is listed as aqueous, for example, aqueous silver ions, just as an example, it means that there's also water present. We have to include water as an entity that we list. That is because water can be part of a redox reaction. It can be a reducing or an oxidizing agent. Okay, anything where it says that it's an acidic solution, we have to include the listing of hydrogen ions. A basic solution, we have to list hydroxide ions. Okay, some of our OAs and RAs are combination of ions or molecules and whatnot. So for example, permanganate and hydrogen ions only act as an oxidizing agent when they are together. Okay, there's a certain few entities that can act as both an oxidizing agent and as a reducing agent. So this is kind of similar to our amphiprotic entities in our last unit, but we have things like water, iron 2, copper 1, tin 2, chromium 2 that can act as both an oxidizing and reducing agent, in which case we have to list them as both an oxidizing agent and a reducing agent, and then we see which it acts as we go through the rest of the steps. Okay, and then we label all other possible oxidizing and reducing agents in the solution. So, our first example is looking at copper metal placed into an acidic potassium permanganate solution. So we have copper metal, and this is a step that we have to do first above these other 5 steps. Okay, so we have, copper metal, which means that we have copper solid. Okay, we have an acidic solution. Okay, so we have an acidic, which means we have hydrogen ions. We have a solution, which means we have water molecules. And we have potassium permanganate solution. Now, when I see potassium permanganate solution, I know that water's obviously involved. I don't need to list water twice. I only need to list it once. Okay, also I know that potassium permanganate, it's an ionic compound and it's in a solution, which means that it dissociates into potassium and permanganate ions. Okay, so I've listed all entities that I need to that could be in this reaction. Then I have to identify my strongest oxidizing agent and strongest reducing agent. Now, you might wonder, how on earth do I do that when I don't have a spontaneity table or anything like that? So I take a look at my chemistry data booklet and I turn to page 7, which has this wonderful chart of different reactions that are half reactions. And again, they're always listed as a reduction half reaction. So one thing I would do first off when I'm looking at this data booklet, first thing I would do here, is I would write down that my SOA is up in this top corner, nice big writing, and it goes down and decreasing in strength, and my SRA is in this bottom right corner and increasing in strength as we go up the table this way. I would also probably jot down my spontaneity rule that SOA to SRA is spontaneous, and then my SOA to my SRA is non-spontaneous. So I would just write spont, just as a little note, so I remember, always on the side of my page as I continue through this unit. So what I see here is that I have this table of relative strengths. Now, if I'm looking for my strongest oxidizing agent, I'm going to start in my top left corner and kind of look down through this column. Now, I divide it into two separate columns in my brain, thinking that this reaction line is our halfway point, and anything on the left side is our SOA, and anything on the right side is an SRA. So when I look at my entities listed on my example, I have copper, hydrogen, water, potassium, and permanganate. So I start looking, and I see it doesn't matter the mole ratio of these things, it just matters that they're present. Now I see right away, pretty close off this top here, that I have my permanganate and my hydrogen ions that are the only two entities listed in this half reaction other than electrons, which is fine. And those two things together make an oxidizing agent. So when I go back to my data booklet here, I list this as, I'm going to do this in a different color. And the way that I would do this is I would write two lines and identify this as an oxidizing agent. Okay? And as I go through, I know, as just for the notes on the previous page, that water is both an oxidizing agent and a reducing agent. Okay? And when I go to copper, let's find copper on the table. I find copper solid and copper solid. Where are you? Okay, copper solid is right here, and he's on the reducing agent side of the table. So again, if this is our halfway mark, he's on the reducing agent side. So I'm going to go back, and we're going to call this guy a reducing agent. Okay, and I can also go back and I can maybe find, it looks like hydrogen on its own can also be an oxidizing agent as well, just on its own. So I'm going to label him just as an oxidizing agent also on his own. And when we take a look back, we see that potassium is a very, very weak oxidizing agent as well. So our potassium ions are a very weak oxidizing agent, which are listed. Okay, so the next goal is, once we've listed these and identified these as either a reducing agent or an oxidizing agent, I can continue on with steps 1 and 2 here. I choose my strongest oxidizing agent and my strongest reducing agent. Now, the way that I do that, again, is to look at my data booklet and to see where relatively these entities exist on our table. Now, essentially what I'm looking for is my oxidizing agent to be closest to the top left-hand corner and my reducing agent to be closest to the bottom right-hand corner. So let's just take a look. I'm pretty sure that this entity up here is going to be my strongest oxidizing agent. So these two entities, permanganate ions and hydrogen ions. And when I go down my table, I see that my copper solid is here as an oxidizing agent and my water is up higher. So my copper is my strongest reducing agent given. Okay, so I have my strongest oxidizing agent and I have my strongest reducing agent. Now, one thing to be very, very cautious of is you have to ensure you're only looking at, when you're labeling these as an OA or an RA, you have to make sure that you're looking at the ion or the atom specifically. So for example, if I'm looking at my potassium ions, when I look at my data booklet, I have to look only at the potassium ions in my data booklet. I cannot look at potassium solid because I do not actually have potassium solid yet in my reaction. Okay, so I have to be specific as to what I'm looking at. Okay, so I've decided my SRA, I've decided my SOA, so I've done steps 1 and 2. Then it says I need to read my reduction half reactions from the left to the right and read my oxidation half reactions from the right to the left. So we're going to start with step number 3, and I'm just going to open up a separate page just to show you what this might look like here. We're going to open up a new page here. So again, we'll take a look and say that our, our reduction half reactions are read just normally from left to right, and we're going to read our reduction half reaction of our strongest oxidizing agent from left to right. So we have MnO4 minus, 8H positive, 5 electrons, and manganese and water. So let's just take a look here. I'm going to split this screen. There he is. So I'm going to just jot it down here. MnO4 minus plus 8H positive gives me my Mn2 positive and 4 H2Os. Now notice that I've just literally copied down this half reaction in from my data booklet right here. Okay, so then when I go and look at my SRA, which we've determined to be copper, which I've scribbled out conveniently. Okay, I have my copper. Now, remember when I just mentioned that we read our oxidizing half reactions from right to left. So we actually read them in this direction. So I read it and re-jot it down from right to left, which is copper solid goes to copper 2 positive plus 2 electrons. So I read the reverse reaction. So again, I've read my reduction half reaction normally, my oxidation half reaction I read backwards, which makes sense, otherwise it wouldn't be an oxidation half reaction. In order for it to be an oxidation half reaction, I have to have these electrons listed as a loss or as a product, right, because it is oxidation. So we assume any ions not present in the table are spectators, which we've done. We did find all of our ions present in the table, even though some of them were not relevant. So once we have this, we can further balance this half reaction. I'm just going to get myself some more room. And again, the most important point when we're dealing with redox reactions is balancing our electrons. So I have 5 electrons versus 2 electrons, which means this is not yet finished. So I look at my lowest common factor here that I can do to multiply these, and it looks like it's just 2 and 5, which means that I'm going to double everything on my top and times everything on the bottom reaction by 5. So I have 2 permanganate ions. I have 16 hydrogens, 10 electrons, which will eventually cancel out, and I have my 5 copper solids. So I combine everything that's a reactant on my reactant side. Then on my product side, I have 2 manganese ions. I have 8 water molecules and 5 copper ions. Again, I would have 10 electrons, which have canceled out from my above reaction. So this is sort of my net overall reaction from this example. So again, my steps are to list all entities, to identify them as either an oxidizing agent or reducing agent based on my chemistry data booklet. I then need to identify my strongest reducing agent and my strongest oxidizing agent. From there, I need to write down my reduction and oxidation half reactions and assume that any ions not present in my table are spectator ions, which is what we've done so far. So let's take a look at another example here. I think I should have enough room here on this slide just to make sure I have enough room to write everything. I think I should have enough space here. So we see that we have potassium permanganate. So again, we have our K, MnO4, and again, these are ions that are dissociated. It is in a solution. Okay, it says it's poured into acidified iron solution. So regardless, right away, we have a solution. Okay, we have an acidified iron 2, which is Fe2 positive, and we have sulfate, SO4 2-, and again, we're in a solution. No need to list water twice, so if you already have it down, no problem. Okay, so we need to figure out my OAs and my RAs in this example. So from my previous example, I already know that my permanganate and my hydrogen ions form an OA, and this is also an OA, and I know that I have an OA and an RA when it comes to water. The rest of them, I can take a look at my data booklet and check it out. So I have iron 2, sulfate, and potassium ions. So again, we have our potassium ions towards the bottom. They're a weak OA, so I can remember that. I have a weak OA. I have my sulfate and hydrogen here, which is an OA. So let's go back here. So these two things can be an OA. My potassium is an OA. Okay, let's see what else we can find. We need to find something to do with our iron. Now remember, iron is listed here. And actually, let's just do some erasing to clean this up a little bit so we can see the example we're looking at. Okay, so we can see, let's do this in orange, that we have our iron 2 here. Okay, and I do believe we have our iron 2 here. So this can be listed as both an OA or an RA as well. When we go back, again, we can list this as an OA or an RA. Okay, so when I take a look and figure out which of my RAs is lowest in the table, and the only RAs that I have listed so far are my iron 2 positive and my water. So when I take a look, I have my iron 2 positive here, and water is up higher. So my strongest reducing agent is going to be, in fact, my iron 2 ions. Okay, so this is my SRA. So let's label that guy. That's what I want. So this guy is my strongest reducing agent. Now, based on memory, I know that my permanganate and my hydrogen ions are basically the third from the top. As a general rule of thumb, don't always follow this rule, but if you see your permanganate and your hydrogen ions, they are almost always going to be your strongest oxidizing agent. There's only 2 other half reactions above that in the table that could be a stronger oxidizing agent than this. So we have our SOA and our SRA, and now we're going to write down our both half reactions, and again we're going to follow the rule. If we have an SOA, we're going to write it from left to right, just like normal, and if we have our SRA, we're going to write it the other direction. So we have our half reaction. Now if I can do this from memory, we have 8 hydrogens plus MnO4- plus 5 electrons gives us our Mn2 positive and our water molecules. Now I'm missing some balancing here. Let's just see what I've missed. Okay, so we have MnO4-, 8 hydrogens, and 4 water molecules. Okay, that helps us out a little bit. Okay, and then we see here too that we have our reducing agent, and our reducing agent is read from the right to the left. So we start with our Fe2 positive, and we go to Fe3 positive plus 1 electron. And in case you don't believe me, we'll go back to the data booklet and we will find it here, which again, this is the direction that we're reading it, from our right to our left. So iron 2 positive turns to iron 3 positive and 1 electron. Okay, again, in order to find our net redox reaction, the most important thing, please do not forget, the most important thing of any redox reaction is having a balanced electron count. So we need to ensure we have the same number of electrons in both our oxidation reaction and our reduction reaction. So it looks like I need to multiply this guy by 5 in order to get 5 electrons. Okay, which means that I have 8 hydrogens. I have 1 permanganate ion. I have 5 iron 2s. Oops. And my 5 electrons are going to cancel out. Then I have 5 iron 3s. I have my manganese ion and my 4 water molecules. So there is my net redox reaction. I've dealt with my different reactions in solution. I've found my OA and I've found my RA, find my strongest reducing agent, list my half reactions, and then come up with my net reaction. So there's this new concept that I have to introduce called disproportionation. Now, disproportionation is essentially a situation where you have a species that is both oxidized and reduced at the same time. Okay, this occurs again when we have an entity that can act as an oxidizing agent and or a reducing agent. It can act as both at the same time. So it's usually we have them as different entities. However, if we do see when an entity is oxidized and reduced, it is called disproportionation. Now, I guarantee you will see this word on a diploma and you should absolutely know what it means. And as we go through this unit, I will definitely go through some additional examples as to what disproportionation is. But essentially, again, it is an entity that is both oxidized and reduced. Okay, so we're going to take a quick look at a few examples here, predicting redox reactions by half reactions. So we're going to use the information to start our half reactions. We're going to balance our half reactions. We're going to balance electrons, and then we're going to add the two half reaction equations. Okay, if they're basic, we have hydroxide ions to both sides, and then we combine our hydrogens and our hydroxides to form water. This looks sort of similar to what we've done so far, except we're going to use it to balance our balance redox reactions with half reactions. So again, this is going to be very similar to the worksheet that you've done already on balancing half reactions. Okay, and essentially you're just pulling out entities that are the same to generate a half reaction and then balance it. So we have C2H5OH going to CH3COOH, and we have our Cr2O7 2- going to our Cr3 positive. Okay, now this is an example where you have to assume that you're in an acidic solution. Okay, and again, this is a situation where we would then start by balancing our oxygens, etc. So in my first half reaction, I balance my oxygens by adding waters. Okay, I have 4 hydrogens, 9 hydrogens on this side, while I only have 4 hydrogens on this other side, so I need to add 5 hydrogen ions. Okay, and then I need to balance my electrons. I need to balance by adding 5 electrons. Okay, that's my first half reaction. I know that I'm going a little bit quickly, but we have already covered this in our previous lesson on half reactions and writing complex half reactions. So, in my next example, I have to balance first my entities that are not oxygen and hydrogen. So I have to have a 2 in front of my chromiums. I have to add 7 water molecules, which means I have to add 14 hydrogens. Pardon me. Once I've added my 14 hydrogens, I have to balance my charge. On my reactant side, I have a net charge of positive 12, and on my my product side, I have a net charge of positive 6, which means I need to add 6 electrons to my other side. When I compare my electron values, I have 5 versus 6, which means that I'm going to need to multiply each reaction by a common coefficient, which means that if I am looking at this right, I would say 30 is our common entity. So we have 6 and 5. If I need to, I can reduce it at the end as well. So I have 12 waters. Might run out of room here. Okay, so again, I can cancel out any sort of common entities that I have on both sides, which means that I can, what did I write down here? I'm not even sure where I got this guy from. What have I done? 12 and 6 and 5. Oh, and 70. Oh, that's right, 70. I'm thinking OH. There we go, 70H positives. Okay, sorry about that. So I can cross out any common entities. So I can cancel out some waters. I can definitely cancel out some of my hydrogens as well. So I'm going to have a net reaction, I'll do this in black, of 6C2H5OH plus my 5Cr2O7 2 minus, plus I have 40 remaining hydrogens, plus 6CH3COOH, no extra hydrogens. I have 10 chromiums, and I have 23 waters remaining. Okay, so this is exactly like what we've looked at before with our half reactions. Okay, at this point, if you are fully confident with this concept, you can go and move on to your assignment. However, I am going to do one more example. I'm going to zip through it pretty quickly just to make sure that we're all on the same page. And for those of you who may need another example, there's another one to go through with me. So again, we have permanganate ions, we have oxalate ions. They react in a basic solution, and we produce carbon dioxide and manganese 4. Now this example I'm going to do on a different page so that I have lots of room to go through my example. Oops, that's not what I wanted. That's what I wanted. Okay, sorry. So we have our permanganate ions. Okay, we have our permanganate ions. We have MnO4 minus, and we have oxalate ions. And oxalate ions are, let's think here, oxalate ions. I need to pull out my data booklet. That's what I thought. OCCO O2 minus. Okay, we have our oxalate ions, and we have a basic solution to produce carbon dioxide and manganese 4 oxide. So we have Oh, you know what? I just need to write this out. Permanganate ions. Produce carbon dioxide and manganese. Oops. Okay. Okay, so this is what I have, and I know that this isn't a basic solution, and I'm just going to pull this so it's a little bit larger. So I'm just going to put a B in brackets so I know if it's a basic solution. Okay, so when I take a look at my next sort of step here, I have my permanganate ions, and they form, and I should move this all over, so I have lots of room on both sides because I know I'm going to have to do some balancing here. Okay, so I have first balanced my atoms other than oxygen, have done that. I'm going to then add 2 water molecules to balance my oxygens. Now I have 4 oxygens on each side, but now I need to balance my hydrogens. I do that by adding 4 hydrogens. Okay, now because I'm in a basic solution, I need to add, I first should add my electrons to ensure I'm balanced on both sides, I guess, which means I have a 0 net charge on this side. I have a positive 3 net charge on this side, which means I need to add 3 electrons. I then add 4 hydroxides, which turn these into 4 waters. And I need to have 4 hydroxides to the other side. So when I write this all out, I get 3 electrons plus 2 waters, because I have 2 waters on the other side that will cancel out, plus my permanganate ions. Giving me this sort of half reaction that I've pulled out. Now my other half reaction, I'll choose a different color so you can see it, what's going on here. And essentially I have my oxalate ion. And again, I don't know why I need to write it closer to the middle here. Forming carbon dioxide. Now again, there's 2 of these because I need to balance my carbons first. Then I have 4 oxygens, so I have 2 and I have 4 oxygens, which means I have 4 oxygens in both cases. I don't need to add any hydrogens because I balanced that. Therefore, I don't need to add any base components, so no hydroxides, but I do still need to balance my charge of 2 electrons. So I have 2 carbon dioxides, 2 carbons, 4 oxygens, 2 carbons, 4 oxygens, and a net charge of -2 on both sides. Okay, when I look at a balanced chemical equation here, again, I'm just going to pick a new color. Looks like this guy is going to need to multiply by 2 and this guy by 3, which leaves me with canceling out my electrons, but I have 6 H2Os, 3 MnO4s, 2 MnO4s, 3 oxalates, giving me 2 MnO2s, and 8 OH minus, and 6 CO2s. Okay, so there's that other example that you can go through. Hopefully you were able to follow along. Again, this is a concept that we did cover a little bit when we talked about writing complex half reactions. So again, you pull out your 2 different half reactions based on what's listed, okay, and then you start to balance them based on what you know, also being in either an acidic or basic solution. Okay, so that is the end of predicting redox reactions. As we go through, like I mentioned, we're going to cover more on disproportionation reactions and what that really means, and we'll take a look at some of those examples. And we're also going to continue on with a little bit of oxidation number coming up next. So you should be able to work on any assignments, and as always, if you need to rewind or go back, please do so to take any notes that you may need from this lesson. Okay, good luck!